In the first part of this video lecture, we have defined what it means to have a product sigma algebra. We made lots and lots of pictures to help us have a better grasp on what is this notion trying to do, because even though the definition itself is very short and very clear, it is quite difficult and abstract to make sense of what it is saying. It can be quite difficult. So that we have been doing some pictures to help us imagine what they're trying to represent. And then we discussed the sections, and we saw that when we have a set, which is a subset of a Cartesian product, we can take a section of that set, and it will be by fixing one point of one of these two sets in the product. And then once we fix that point, the value of that point, then the section will be a subset of the other sample space. And we saw also that functions, if we have a function that depends on the product space, okay, then we can, if we fix one of the variables, then what we get is a function that only depends on the other variable, and we call that a section as well. And then we stated this lemma and insisted that this is an important lemma, that if the subset we take in the previous definition, if the subset is measurable with respect to that product sigma algebra, then the sections are measurable with respect to the space where they belong. And likewise, if a function from the Cartesian product to another space, here the space is R, before there was no requirement on this space, then if that function is measurable with respect to this product sigma algebra, then we can fix the variable, and for each value of the variable that we fix, we get a function of the other sample space, and that function will be measurable with respect to the sigma algebra of that space. And now in this video lecture, we're going to prove this lemma. For the proof, we're going to first consider the first statement here. The first statement, it says Ex is F2 measurable for every value of x. Of course, we don't need to consider Ey because the argument will be completely asymmetric. So we want to show that Ex is measurable with respect to the sigma algebra of the second sample space. And how do we prove that? Well, fix some x, yeah, because this we want to prove this for each x fixed. So let's suppose x is fixed now, and we want to consider the collection of subsets of this Cartesian product such that the section, once we fix x, the section is measurable with respect to the second sigma algebra. Of course, if we take a Cartesian product which is already, we take a rectangle. So if we take a set which is of this form, it is A Cartesian B. So you can think it is of this form, where here we have A, and here we have B. So if our set is of this form, then this is true. So this is what this sentence here is saying, that this class here of subsets of the Cartesian product whose section by x is measurable in the second space, this is this contains the rectangles. And why does it contain the rectangles? We can just take a look here and see what we have. If x is outside the set A, then the section will be empty, and empty is in the sigma algebra F2. So the property that we claim, it will hold. And likewise, if x now is in the set A, if x is here, and we look what is Ex, then Ex will be exactly equal to B, and B by assumption is in F2. So if we go back to what was being said that what is the claim? The claim is sets of this form, they have this property, because the section here was in F2 in both cases. Why are we insisting on this approach? Well, you will remember we did it very much in the second week of this module. We did very much consider classes of sets that satisfy the property that we want. And in the end, what we do is we show that the class is actually large. And this is what we're going to do. We're going to show that G is a sigma algebra. And if G is a sigma algebra on this sample space given by the Cartesian product of omega 1 and omega 2, then, well, if it's a sigma algebra, then it contains the sigma algebra generated by this class, because it contains this class. And the sigma algebra generated by this class is exactly the product sigma algebra. So if we go back to the statement of the lemma, it assumes if E is in this sigma algebra, then EX will be F2 measurable. And this is exactly what we are concluding. If we can show that G is a sigma algebra, then G will be equal to the whole sigma algebra, which means every set E in this family will have this property. And this is exactly the property that we are trying to show. So this is just to explain that all that remains is to show that G is a sigma algebra. Well, how do we show that G is a sigma algebra? Well, we're going to check all the properties of sigma algebra. Before that, let us just make some two observations that will be used in this proof. The first is, suppose this is my set E, and for a fixed value of x, we have EX here. What happens if we take the complement of E? So the complement of E will be everything except this green lake here. So this will be the complement of E. And when we take the section of this complement, this section will be exactly what the complement of the previous section. So here this will be the complement of the section, and it will coincide with the section of the complement, which is what is being said here. So if we take E, the complement, which means we take this set here, and we take the section by X, this is the same thing as first taking the section by X, and then first taking the section by X, and then taking the complement. So we're going to use this in the proof. And another thing we're going to use in the proof is the following. If we have a sequence of sets, let's say E1, E2, E3, E4, etc., then when we take the section of these sets by a certain X, then the section of the union of these EIs will be the same as taking the section of each of these EIs and then taking the union over I. So this is what these two properties here are saying, and we're going to use them in the proof. So to check, we have to check three things to say that this is a sigma algebra. Of course, omega 1, omega 2 is in G, right? Because if we look at the Cartesian product omega 1, omega 2, and we take the section by X, we get omega 2. Yeah? This is a bit trivial. I cannot make a picture of it. We have the whole space. Now we fix the value of X and we take the section. What we get is the second space, omega 2. So this is what it's saying here. And omega 2 is in F2 because F2 is a sigma algebra. And now to check the second property, well, we take a set E, which is in the sigma algebra G, which means because it's in the sigma algebra G, it means the section by X is measurable. But now if we take the section by X of the complement, then this will be the complement of the section by X, and this will be in F2. Why would this be in F2? Well, because EX is in F2 by assumption, okay, here, and F2 is a sigma algebra, it's closed under complements. Okay, and that means EC, so EC is in G. So this is the conclusion that we get, is that this EC is in G. And why that? Well, because taking the section by X, we got something which is in F2. And now finally, we want to check the third property. And well, we take a sequence of sets which are all in G. What does it mean to be in G? Again, well, it means that if we take the section by X, we get something which is in the second sigma algebra. And then, well, each one of them is in the sigma algebra by definition. And if now we look what is the section of their union, by the previous argument that we showed already, it will be the union of their sections. And this will be in F2, because each one of them is in F2, and F2 is a sigma algebra, so it's closed under countable unions. So we can conclude that their union is also in G, and this concludes the proof that this is a sigma algebra.